Hi everyone, and welcome to our next video. I'm Miss Gogerty, and today we are going to continue our conversation, or in this video, we're going to continue our lovely conversation about derivatives of inverse functions. So specifically, we are going to add on the derivatives of inverse trig functions. So it's going to look a little different from our last video, in just that in the beginning here, we are going to derive what are the derivatives that we need to know. So hopefully you have your note sheet 310B up. If not, make sure that you've got your notes ready, and here we go. So in our first example, we're looking at, we have y equals sine inverse of x. And what our job here is to do is to find the derivative of this inverse trig function using implicit differentiation. Well, at the moment, if we started this, it doesn't look like we'd have to use implicit differentiation. So we're going to write an equivalent statement here based off of our knowledge from trig. So one of my favorite things to teach. So let's start off with looking at an equivalent statement, okay? So let's just move this equation around so that our input value is going to be a y value, okay? And in order to do that, all I have to really do is take the sine of both sides, and we should be able to agree that the sine of y is equivalent to x, okay? Well, now that we have a sine function, we know the derivative of sine. So if we take this a little bit further and using our implicit differentiation, then I should be able to say, well, the derivative of sine is cosine. Okay, and then I'm going to have to use the chain rule, right? And the derivative of y is going to be dy dx. And the derivative of x is 1. Okay, so following this idea, I can get that the derivative of y is going to be 1 divided by the cosine of y. Now, the harder part here that we have to consider is, well, what the heck is cosine of y? Okay, how can we come up with a way to evaluate that and look at it a little bit closer? And that's going to be to come back and look at sine y equals x. And think back to, goodness, geometry, for goodness sakes, when you learned the definition of sine. Okay, and when we learned the definition of sine and then expanded on that definition in pre-calculus, we're looking at this thinking, okay, well, if I have a right triangle, all right, it's been a while since we've looked at this. I'm looking at an angle measurement of y. Okay, so I'm going to fill in y. And right now, x, what does x mean? What's its definition if we go back old school to sine? And hopefully you're with me if I say, well, x is opposite over hypotenuse, right? Well, on our triangle then, opposite would be x, hypotenuse would be 1, and you should be like, wow, I remember these days, right? And can you come up then with a statement for the third side? So using the Pythagorean theorem right now, can you tell me the length of this other leg, right? And so hopefully we can get to the point, while using Pythagorean theorem, I'd have leg squared plus x squared is 1, right? Plus x squared is 1. I need to find out how long is the leg, so 1 minus x squared. The leg, oops, sorry about that. The leg is the square root of 1 minus x squared. Now, why do I want to know that information? Well, come back down to here. Can you tell me now what is cosine of y? If we look at this picture up here, we now have a representation for cosine of y. And the cosine of y, whoops, sorry about all those colors, would be 1 divided by, well, cosine would be adjacent over hypotenuse. So square root of 1 minus x squared. So what did we just find out? Okay, well, if you follow through this, right now, this is the derivative of our original problem, right? As soon as we rewrote this with sine of y equals x, we're still looking at an equivalent statement. So when we found the derivative in the next step, all we're doing as we work our way down here is writing equivalent statements of the derivative. So when I look at my final result, if y was sine inverse of x, then dy dx, or y prime, whatever way you want to write it, is going to be 1 divided by the square root of 1 minus x squared. And my friends, this is a derivative that you must know, okay? When I say you must know it, I know my students, we have a list that is at the back of our notebook that we keep adding derivatives to, and I'm hoping the rest of you are as well. This is going to be something that comes up quite often, and we don't want to have to derive it every time. So from this point on, if you're asked for the derivative of sine inverse, it's important that you just know it's 1 divided by the square root of 1 minus x squared, okay? So the next two that we're going to look at, I would encourage you right now to actually pause the video and try to do these two derivatives on your own. They follow exactly what we did above, and I think it would be really good on your part to practice your implicit differentiation, to practice your derivative of trig functions, and to see, can you derive the derivative of cosine inverse and the derivative of tan inverse? So please, please, please pause the video and try it on your own. Okay, welcome back. So let's see how you did. And I'm going to walk you through one more, and then I'm going to see if you can just get the final answer, okay, of tan inverse. All right, so we got to start with, I don't know the derivative of cosine inverse, okay? So I need to change the way it looks so I can use implicit differentiation and change it back to a function that I already know the derivative of. So I'm going to do that by simply taking the cosine of both sides, so that I have cosine of y is equal to x. So here is my equivalent function, okay? I haven't done anything otherwise yet. So now I'm ready for the derivative. So the derivative of cosine is negative sine. Now I have to take the derivative of the input. So I'm using implicit differentiation, chain rule, okay? And so that's going to be dy dx. The derivative of x is 1. So if I solve for dy dx, or y prime, I end up with 1 divided by negative sine of y. Now, I don't know yet what this value is, so I'm going to think about all the things I've learned in the past, and it's been a lot. You've learned a lot of math while you've been in school. So I want to examine the meaning of this, okay? And when I say let's examine that, I'm going to draw my nice right triangle. Oh, it was our friend for a long time. Put my y in here because here's the angle I'm evaluating. Now, cosine equals x. All right, well, what does x mean in this case? And that means adjacent over hypotenuse. So the adjacent leg is x, the hypotenuse is 1. I'm going to do some Pythagorean theorem fun, and I'm going to find out that this side is the square root of 1 minus x squared. So let's come back down now. Using this information, let's evaluate sine of y. So sine of y is opposite over hypotenuse. So that allows me to get to the point where dy dx is equal to negative 1 over the square root of 1 minus x squared. Okay, so what does that mean? Okay, well, if y is cosine inverse of x, that's what I just started with, then y prime, or dy dx, whatever you want to call it here, they're all meaning the same thing, is negative 1 over the square root of 1 minus x squared. And here is another derivative that I need to know. Cosine inverse, its derivative is negative 1 over the square root of 1 minus x squared. So very similar to sine inverse, but it's negative. So we got to be careful with that. Okay. All right. So if you haven't already tried tan inverse, please pause the video. It's really important for you guys to try this on your own. Okay. Okay, so welcome back. How did you do? So if you take a look at this, did you end up finding out that the derivative of tan inverse is 1 over 1 plus x squared? okay? If you need to pause the video right now, please do so that you can follow the work that I have on the screen, okay? So started with taking y equals tan inverse of x. I needed to manipulate that. I don't know the derivative of tan x or tan inverse of x, so I needed to change the way it looked so I could just have tangent. Then I used implicit differentiation in order to find the derivative of tan y, and then kept on just manipulating until I got to a point where I needed to evaluate what the heck is secant squared y. So I had to come back to my old school knowledge on the right triangles and what tangent means. This is opposite over adjacent, so I had an x over a 1. Used the lovely Pythagorean theorem to get my hypotenuse, and then just plugged those values into secant squared y, and there is my result, okay? So, my dears, as we're looking at this, it's really important for us to realize that the 3 most important derivatives of inverse trig functions for you to know are the 3 that we just derived. So the derivative of sine inverse, derivative of cosine inverse, derivative of tan inverse. Those need to make your list of easy access derivatives and ultimately memorized, okay? Now, as for the other 3, secant inverse, cosecant inverse, and cotangent inverse, here they are ultimately, and you're going to also see them in your book if you use your book and read over the notes. But in general, when it comes to homework problems, we would just expect you to go and look these 3 up, okay? Now, this table that I'm giving you right now is already using the chain rule and putting it into the end result. Your book looks a little different. So if you're wondering why your book's formulas are any different, it's just because they're using the chain rule to say you have to take the derivative of the angle, okay, or the input. So don't get too wrapped up about that. I just, once again, need you to be aware that these 3 inverse derivatives exist. And when I say to be aware of them, that you know where to go find them if you have them in a homework problem, okay? Now, I think the popular question is going to end up being, are you going to put this on a test? If we were to put it on a test, we would definitely be giving you access to these. Now, since we're in remote learning, you're going to have access to these anyway, right? So let's go a little further. The way to get these 3 would be very similar to what we were just doing on the previous screen. The only thing that comes up is a little different is you have these absolute value of u's or the inputs, the absolute value of the inputs, and that is coming from needing to restrict our domains and looking at basically where our inverse trig functions exist. Your book does a nice job explaining these. So if you actually are inquisitive to know, like, I'm not really totally sure why that absolute value of u is there, telling you go and look in your book, it's all good. So domains are restricted to make these functions. We remember that, I hope, from when we were graphing secant and cosecant and cotangent inverse, actually even sine and cosine inverse back in pre-calc, okay? Another little thing to make sure that we're highlighting and just keeping at the forefront of your minds, sine inverse and arc sine mean the same exact thing. So on an AP test or any test in general, if you see arc sine come up or arc cosine or arc tan, they mean sine inverse, cosine inverse, and tan inverse, okay? So please, please, please make sure you commit to memory these 3 inverse trig derivatives, okay? And so with that, let's practice a few, all right? So I would like us to go through example 2 and 3 together, and I would like you to try on your own the last one and then come back and check your answer, okay? So for this first problem, find the derivative of sine inverse of t squared, okay? So when we're finding the derivative, remember we're using the chain rule. I need to find the derivative of the overall function and multiply that by the derivative of our input, okay? So the overall derivative of sine inverse is going to be 1 divided by the square root of 1 minus our input squared. Okay, now if you need to look back, you go for it. I can find it right up here. Now, once again, I don't want you getting confused by this. This means 1 over the square root of 1 minus u squared, and you're multiplying it by the derivative of the input. Remember what I said, this is already combining the chain rule in the problem. So coming back down to my problem, I now need to multiply it by the derivative of my input, my chain rule. So that would be a 2t, right? The derivative of t squared, 2t. So my final answer on this would be 2t divided by the square root of 1 minus t to the 4th. Done. Okay. So check, we got it. All right. So moving along, find the derivative of y equals tan inverse of the square root of x minus 1. Okay, so chain rule is coming again. We need the derivative of the overall function multiplied by the derivative of the input. So I need to go back and look at what was the derivative of tan inverse. And the derivative of tan inverse is 1 divided by 1 plus the input, which is square root x minus 1 squared. Okay, now so far, this is only the derivative of tan inverse. Okay, so now I need to take the derivative of the square root of x minus 1. So I'm hoping that we can think of this as x minus 1 to the half. So when I multiply by the derivative of x minus 1 to the 1/2, I'm going to not only use the power rule, but don't forget you technically need to take the derivative of what's inside of here too. So we're doing the chain rule again. It just so happens that the derivative of x minus 1 is a nice little 1. So if you forgot it, it wouldn't make a difference on this particular problem. But if this had been pretty much linear without 1 is the slope, or if it would have been a quadratic or something, you need to make sure you're still doing the chain rule on that derivative. Okay, so technically speaking, we could be done here, but let's practice our algebra a little bit. All right, so y prime is going to be 1 over 1 plus, well, what happens here when you square a square root? That's kind of nice. We're left with x minus 1. And then I've got a 1 over 2. Let's see. This lovely goes to the denominator. So I'm going to have a square root x minus 1. And then I just have times 1. Okay, so if I start simplifying some things up, those 1's cancel. Okay. And now otherwise, if I multiply this together, I get a nice 1 over 2 times x square root x minus 1. Now, I know in my classes we've been talking a lot about how far do you really have to go. I do want you to just see from time to time like our manipulation with our exponents and just simplifying fractions. It's still good for you to keep those skills strong, okay? So my next problem is a little bit more in depth, and so I want you to please pause the video and try it. When you come back, the answers are going to just be here, okay? So please pause, try it out, and I'll see you in a minute. Okay, welcome back. Take a look. How did you do? Okay, so this one had more algebra manipulation, but oh my goodness, even the derivative, I'm going to dare say it was fun, right? And some of you are like, fun? What is wrong with her? Okay, so first thing we started with, what is the derivative of cotangent inverse? Okay, and the derivative of cotangent inverse is a -1 divided by 1 plus the input squared. So here's my input. It's coming down into there. Okay, now that's just the derivative of cotangent inverse. All right, that's the setup. Now we have to use the chain rule to find the derivative of the input. So as I'm doing that, the derivative of the input is actually, you know, the quotient rule, right? So low D high minus high D low over low squared. Now that's just my way of remembering it. And otherwise, if you've memorized the quotient rule, it's all good, but we're taking the low times the derivative of the high. Well, derivative of 1 is 0 minus, well, the numerator times the derivative of the denominator, okay, over the denominator squared. All right. It's kind of nice because when you multiply by 0, that goes away. And now the rest of this is all about algebra reducing, okay, simplifying in our problem. Down here at the bottom, I am a little worried that some of you might look at these two being multiplied together and try to make it way more complex than it is. When we're multiplying these two, you're literally taking this term and distributing it onto both. I don't want to expand x squared plus 1 squared. I don't at all, especially when I see this has the same denominator. When we multiply these, our result is going to be a 1. Okay, so everyone, I hope that this helped you, and I think you guys should be good to go now with your homework from 3.10 or from section 10. So good luck. Let us know if you have any questions and need any help, and we'll see you later. All right, bye everyone.